So, hello everyone. So, we will continue with the topic yarn hairiness, and now we will discuss different techniques of measurement of yarn hairiness. As we have discussed in last class that the techniques, there are basically two different techniques are there. One is measurement of yarn hairiness by number of hairs beyond certain specified length, and another technique is that measurement of total length of hairs beyond certain length. Okay. So, that both these methods, they have their positive points and negative points. This detailed we have discussed in last class. Now, we will discuss the exact measurement technique. First is that Shardley yarn hairiness tester. Okay. Here we actually measure we count the number of hairs longer than a pre-selected length between 0 to 10 millimeter, and usually if we see it is a 3 millimeter. Okay. Now, suppose this is yarn. Okay. Here we have different lengths. Now, what we want? We want to measure the length of number of hairs. So, these are in on the both sides. We want to measure, suppose this one is the length 3 millimeter. So, it will count whatever whichever hairs are more than the 3 millimeter length, say 3 millimeter. So, this will keep on counting, this is 1, it will count 2, 3, this will be not be counted 4, say it will not be counted 5, this is just below 6, 7 not counted, 8, 9 not counted, 10, 11 in this way. So, it will keep on counting the number of hairs per unit length. Suppose this is 50 meter length of yarn has been passed. So, it will there will be photo sensor, this will count. Now, the condition, that situation here is it will only count the hairs which is beyond 3 millimeter, and yarn is not one dimension or two dimensional material, it is a 3D material, it is a almost, if we see, circular in cross section. Suppose if we draw this yarn cross section, this is the cross section, this is yarn cross section, this same yarn's cross section. Now, the hairs are like this. Hairs are not in a particular direction. This is actually, these hairs are covering the entire surface. Now, what is happening here? This sensor here, photo sensor, it actually sends only from one point, not even surface, only from one point. Suppose this is a sensor, it is placed beyond 3 millimeter. Suppose here it is a 3 millimeter sensor. Now, this sensor is only sensing whatever hairs, the yarn is actually moving in this fashion. This is the movement, yarn movement direction, yarn's direction. Okay. So, in this picture only this hair or this hair or maybe these 3 hairs will be counted. Okay. And if there is some smaller hair here, this will not be counted, that is actually we want, but these 3 hairs are counted, the signal will be, the number of hairs will be 3, but actually there are large number of hairs. Even this hair will not be counted, because this is not coming in that range. Okay. So, that means is it giving the correct result. So, the count what we are getting, say 100 hairs per say meter or 1000 hairs per meter, whatever may be the count. Are we getting the exact count of the hair, number of hair? No, we are not getting. We are getting the indication of hairs with an assumption that the hairs are actually covered uniformly throughout the yarn surface. Okay. Same we will see, same is the case of the, if we want to measure the fiber hair length. Okay. So, this is the, here one should not get confused that this gives the total number of hairs, it is not the total number of hairs, it is the hair only within this zone, only within this zone, and rest hairs are not counted, but the condition that actually for comparison or for some grading this is enough. Okay. Because with the assumption that the hairs are uniformly distributed throughout the surface. Okay. Now, so in Sharley Heerin's tester, what we do here, it is usually it measured the hairs beyond whatever the length, the more than 3 millimeter, it counts the number of hairs. Okay. But it another set, it can actually be varied. There is a two set of rollers are there. One is a fixed roller, which is fixed at the 3 millimeter the length beyond the yarn surface. Another one, it is a variable which varies from 0 millimeter 0 to say 10 millimeter, maximum 10 millimeter, and it counts the number of hairs. So, it consists of a light beam shining on a small diameter photoreceptors opposite to it. So, in that picture what we have seen here, there will be one light source. So, if suppose it is a light source is there, light source is there. So, this light source and in other side there will be photoreceptors. This photoreceptor will actually get the signal. Okay. Now, while the yarn is moving, suppose there is no here this light totally it will reach to the photoreceptor, but in case of hairs coming in between, so that obstruction will give indication that there is only one hair. Okay. Now, the another problem here is that, so very high density hair concentration, in that case if there are two hairs coming together, this may give signal of one hair, but in any case this gives rough idea about the number of hairs. Okay. So, the light beam, it consists of light beam and a photoreceptor of small diameter light beam. So, yarn under test is run between the light and the photoreceptors. When it is moving, the hairs pass between the light and receptor, the light beam momentarily broken, okay, and the electronic circuit counts the interruption, it counts the number of interruption. So, as one hair. So, if it is interrupted once, maybe by single hair or maybe a cluster of hair, it will be counted as one hair. Okay. So, that one hair, only the hairs within the aperture are counted. If it is below, if it is beyond that aperture, as I have mentioned, so because the yarns are covered with the total hairs throughout the surface, because total number of hairs is proportional to this count. Okay. Now, this is the instrument, here we have two yarn paths. This yarn path at the bottom it is called the fixed yarn path. So, here the yarn will move and this is the guide, and here this is the aperture distance where light passes through that, and the distance between this aperture and this guide it is fixed here, it is a 3 millimeter. Now, the 3 millimeter distance that may vary depending on the diameter of the yarn. Okay. So, that it has to be initially it has to be actually set first, okay, calibrated that initial distance based on the diameter of the yarn. So, for coarser count yarn we have to move this guide little bit further away, so that the outer surface, this top surface of yarn and this aperture, this distance remains 3 millimeter. And as the yarn moves in this direction from left to right, so this hairs will be actually will give obstruction here in the light beam, and it will this will be counted. Now, if we want to measure the hairiness other than the 3 millimeter, we have to select the variable path, where another guide roller is there, but which is movable guide roller. Here it is a fixed guide roller, this guide roller is movable and it is between, so 0, and we can set at anything between 0 to anywhere between 0 to say 10 millimeter. So, that if we want a higher length of hair want to measure, so we will shift this guide roller little bit above this. So, that will take care of the. Now, let us see the animation here. Now, it is a fixed path, that means now it is moving, the yarn is moving. Now it is 1 obstruction, 2 obstruction, 3, 4, 5, and it is not, this one is not obstructing, 5, 6, those obstruction are coming under this aperture are counted. Okay. But it's you can see that this is not counting the hairs below or in other side. So, this counter, so for certain length it has count, it is a 19. So, 19 hairs that is are more than 3 millimeter of length. Okay. That actually gives us the idea about the hairiness. Okay. Now, we will use the variable path. Okay. This is a variable path for different, say like 10 millimeter, we want to measure number of hairs beyond 10 millimeter. This is only one hair, this one will be counted. Now, it is moving, rest other are, now it is 2, now this one will be counted only, it is 3. So, in this way this one will be counted, this is 4, that means there are 4 hairs beyond 10 millimeter length. So, that way we can get fair idea about the length of hair and also the number of hair. Okay. Now, we have shifted it to another distance, it is a 9 millimeter. Now, same yarn if we pass, so accordingly we will get different count. So, earlier it was 4 hairs beyond 10 millimeter, now we are we can observe it is basically around say 6 hairs beyond this. Okay. So, in this way we can get the detailed idea about the number of hair and length of the hair distribution. Okay. Now, it has been shifted to another length, so say 8 millimeter. So, for 8 millimeter again we can test. So, this way this variable length works. Okay. So, it is counting the hairs beyond that. So, same yarn we are passing again. So, it gives the idea it is a 7, say 8, okay, 9, 10, it will give say 10 hairs. Okay, 10 hairs. Okay. Now, if we can see it is an 8 millimeter. Now, we have shifted little bit more 7. So, it should be more than that. Okay. So, that way we will get total distribution in the hairiness, but here we cannot test more than one setting at a time. Here we have to change the setting, we have only one setting at a time we have to take. Okay. So, 7 millimeter it is giving 11, say 12, 13 it will be 12 and 13 it is there. Okay. Now, if we say now that is the end of this. So, we can test at other 6 millimeter, 5 millimeter, 4 millimeter, in that way we will get the result. Okay. Now, this yarn hairiness tester, it has got two sets of yarn guides that we have discussed. Lower set leads the yarn over a guide at a fixed distance 3 millimeter from the receptor, because the guide roller actually set the distance. The upper set it leads the yarn guide, actually it is a movable, okay, at different distance from the receptor, okay, between 1 millimeter to 10 millimeter. Okay. The total number of hairs in a fixed length of yarn is counted. Okay. So, for say fixed length, say 100 meter yarn, for 100 meter we can count the total number of hairs. Okay. And if we know the speed of testing and if we know the count time, so we can calculate the number of hairs per unit length. The next method is that it is a Zoegal hairiness tester. Now, its principle is exactly same as the Shirley hairiness tester, but the main problem with the Shirley hairiness tester, we can get the data one hairiness, one particular set of hairiness at a time. Okay. If we want to test 3 millimeter and beyond, number of hairs of length 3 millimeter and more, then we have one test, we have to have one test. Then if we want to have say 4 millimeter, 5 millimeter, then we have to have repeated testing. But this method gives the total range of hairiness length. It also measures like Shirley hairiness tester, it measures the length of hairs. Okay. So, the aperture counts the number of hairs at a distance from 1 to 25 millimeter from the yarn edge. Okay. Suppose this is the yarn edge and there are hairs. At different. So, in this, in Shirley what we have observed, there is only one that photoreceptor, okay. But here we have number of photoreceptor, typically 12 photoreceptors are there of different length from 1 millimeter to 25 millimeter, and they get signal simultaneously, and totally at in one go, one test we can get the total distribution of number of hairs of different length, okay, different projected length. Now, the measuring principle, as I have mentioned, it is exactly same as the, it is similar to a Shirley instrument, and here we have total 12 sets. So, there are set of photocells, okay. Here typically it is 12 at different distance from the yarn surface, 1 millimeter, 2, 3, 4, 6, 8, 10, 12, 15, 18, 21 and 25 okay, millimeter from the yarn, and that initial setting we can do by proper initial adjustment. Now, this is the animation and the picture, it shows that here we have different photo sensor. Okay. This is a photo sensor, and here when yarn moves similar to that of Shirley hairiness tester, this also record the number of hairs. Okay. Now, you can see here, now yarn is moving Now, counter has started at different length 2 millimeter, 4 millimeter, 6 millimeter like that, okay. And this is giving result number of hairs. So, it is exactly in the same way, but we are getting all the data at a time. Okay. So, and here this is actually cumulative total, this one will give us the total idea of the number of hairs beyond that length. Okay. So, there are, that means it is there are 27 hairs beyond 2 millimeter, 24 hairs beyond say 4 millimeter. So, between 22 to 4 millimeter if we want to measure it, we can also measure just by subtracting. So, this gives the total idea, overall idea of the length of the hair, which is very important, because it is the length of the hair which is very important, and it is the number of hairs, number and length of hairs, and it gives the total distribution. Okay. And in this method the yarn is illuminated from the opposite side of the photocell, and as the yarn runs past the measuring station, the hairs cut the light off momentarily, exactly same as the Charley hardness tester. The instrument measures the total number of hairs in each category for the set of tests, and typically the fixed speed is kept, it is a 50 meters per minute, that is important. If I have already discussed, if we increase or decrease the speed, then it is not comparable. Okay. Now, let us see, this is the yarn, suppose this yarn, if it is running at say 50 meter per minute, 50 meter per minute, this yarn will give certain result, and 50 meter per minute it's sufficiently high for to have quick test, and sufficiently low so that the yarn the hairs does not get distorted. Okay. But suppose I want to finish my test quickly, I have increased to 500 meter per minute. The thing will be that these hairs will be, due to the air drag I have mentioned, this will try to have different orientation, and this will give entirely different result. That is why this the speed in this instrument is specified. If we change the speed, total hairiness reading will be different for same yarn. So, that is why it is recommended we must run the yarn at a specified speed. Okay. So, that if we change the speed, we can get altogether different result. So, the 0 point it is important. It is important not only for this also, but for the Charley hardness tester. 0 point setting is important, that is the position of the yarn edge relative to the photocell is adjusted, that we have to adjust perfectly. Okay. A further set of photocell is used for this to locate the edge of the yarn. So, we must locate the edge of the now how to locate the edge. So, that it is basically it gives the point like here the how to locate this edge, it this photocell will locate where the density, that light, the density is very high, that means light will not pass, and after just beyond this edge light will start passing. Okay. So, that edge detection is done by a separate photocell. Okay. This edge as it is important, then only that the reference, this is ultimately this will be the reference point. So, beyond this reference point, then it will start counting or measuring the length of the hairs. And next technique is that it is a Wooster tester. Wooster, actually this is a an attachment with Worcester evenness tester, and one should not get confused that Worcester evenness tester that we will discuss later, it works on capacitance principle, but as because it is attached with the Worcester evenness tester, people may get confused that it works on capacitance principle, because in capacitance principle we cannot measure the hairiness, because here the technique is that it is a again light principle, it works on light scattering principle, but it is an attachment, but it is independent instrument, okay. Optional attachment of Worcester evenness tester, but as the software is there in Worcester, which gives different types of characteristics like different types of curves, graphs like that spectrogram, histogram, or this type of different mass variation diagram, okay, that is called diagram, it is called. So, this type of this is for the mass variation like evenness, and similar variability variation, similar curves we may get also for hairiness also. So, it works on IR light illumination, okay, and its light scattering principle. A parallel beam of IR light illuminates the yarn as it runs through the measuring head, okay, and the direct light is blocked from reaching the detector, and that is important. So, if there is no yarn, suppose the yarn is absent, the instrument will show it is nothing, no light is coming, okay. Only light that is scattered by hairs protruding from the main body of the yarn reaches the detector, okay. So, light, now this I will explain here. Suppose it is a light source is coming, this is a light source, okay. Now, and here we have something which is blocking, this is block, okay, which is light stopping, which blocks the light, and somewhere here we have receptor, light receiver, okay. Now, in normal case there is no, and yarn passes through this point, this is the yarn path of the yarn. Suppose there is no yarn, in that case what will happen, light will directly projected on this stop and light will never reach in the receiver, okay. This is the receiver. So, this stop will actually stop the light. Now, after that what we are doing, suppose this is one filament yarn or yarn with 0 hairiness, it is moving. Again what will happen, this yarn will block light to some extent, but beyond that whatever light is passing, this will be blocked again. So, in that case also nothing is reaching here, no light is reaching here. So, that means it shows that there is no hairs. In next case, a yarn with hairiness, this hairiness is it is coming. Now, what will happen, this the yarn has got two portion, two distinct portion, one is its body, another is hairs. The body of the yarn, core side of the yarn, it is as good as the filament, it will act as a filament. So, it will block the light will not pass, but when the light will fall on this hairs, these hairs, okay. The hair when it is coming here, this hair will start actually scattering the light. Light will get scattered by these hairs. Now, again the issue of the totality, I am drawing the cross section here. Here this is the cross section. When the yarn is moving, suppose the light is, this is the light. Okay. Now, light will scatter all the, it will get scattered by the hairs which are coming on its way. Now, all this hair will come, but this hair may not come, just opposite side, and also this hair if it at all scattered, this may be blocked again by the body. So, but whatever the amount of the light, quantity of light it scattered, it is definitely proportional to the number of hair, total length of the hair. Now the ear, that this light is scattered throughout the surface. So, this the total quantity of light it is scattering, it is proportional to the length of the hair coming across the light source, okay, light path of the light, and this will get scattered, and with the help of some this lens arrangement, this will be actually taken away. So, this type of lens arrangement will be there, and this will again be converged here, and it will fall on the receiver. Okay. So, then the quantity of light received by the receiver is proportional to the total length of hairs projected. So, here this is the transmitter which transmits the IR light, and it is through this optical arrangement, this is the parallel light is going, and it is blocked by this top arrangement, and this is the actually this is the stop arrangement. Here it is again it is blocked by this arrangement. Now, this will be blocked when there is no yarn and when there is yarn without any hairs, but as the hairiness is there. So, this hairiness will actually scatter the light, this scattered light will get again converged here, and receiver will receive the light. Now, let us see the animation here. Now, this light is diverging, light is coming, and due to this lens arrangement, lens 1 it has become a parallel ray of light, and first iteration is when there is no yarn, and it will be it is blocked by this blocker, it is blocked here. Okay. No light is going to the receiver, intensity of receiver I2 is I1 is 0. Now, again the yarn without any hairiness is coming, it is like filament yarn. When yarn moving with no hairs, so nothing will change. Okay. It is actually again the intensity of light here it is 0. So, it will show there is no hair. Now, the yarn with hairiness is coming and now the light will start getting scattered by the hairs, and this scattered light will fall on this optical lens system, lens 2, and then again it will be converged and it will fall. Now, this light, the intensity of hair is I 3 is proportional to the length of the hair. What we are getting here, we are not actually measuring the length, but we are getting an idea which is proportional to that intensity which is proportional to the length of the hair. And this intensity, how are you getting the length? Because it has been actually gauged from prior data, this has been actually gauged that much intensity means this is the length of the hairs. So, the amount of scattered light is then measured, it is a measure of hairiness, it is converted to an electric signal by an apparatus, by the apparatus, it is thus monitoring the total hairiness. And the instrument gives a data which is known as the hairiness index, that means total length of protruding fiber with a reference to the sensing length. What is the sensing length of 1 centimeter of hair? That is important. Total length of hair in centimeter divided by the length of yarn in centimeter. So, that is why this is dimensionless, centimeter by centimeter. That means higher H value means higher length of hair protruding. So, H value of say 5 means in 1 centimeter yarn. So, say H value of say 10. What does it mean? Suppose we are taking say 1 centimeter yarn, 1 centimeter yarn, and it is the, if we take the total length of the hair, if we add together total length, it will become 10 centimeter. So, 10 centimeter is the total length. So, higher H value means higher length of hair. So, as I have mentioned that its attachment with UT3 Wooster tester hairiness evenness tester 3. So, it gives the hairiness evenness tester gives the diagram mass variation, here it gives the diagram of hairiness variation. UT3 gives the spectrogram of mass variation, here it gives the spectrogram of hairiness, and there UT3 gives the mean value, here also it is a mean value of hairiness similar to that of mass variation. Now, we will discuss the measurement of hairiness of fabrics. There are few techniques. The surface hairiness is basically it is a indication, it gets higher the yarn hairiness, that will result higher surface hairiness, and it can be measured by different techniques. One is that low compression testing. Now, the fabric hairiness, suppose we have two fabrics, this is fabric 1, fabric core, and it has got hairiness, these are the hairs on the surface. Another fabric, suppose there is no hairiness. Now, how do we get the indication of hairiness in the fabric on the surface of the fabric? If we test the compressibility at low pressure. So, the fabric with higher hairiness will give higher compressibility, but this fabric A will give higher compressibility and fabric B will give least compressibility, it will not be compressible. So, this by knowing the compressional value at low pressure will give idea about the presence of surface hair. It is called low pressure compression testing. Next is the laser counting of protruding fibers. It is similar to that of the Worcester hairiness tester of yarn. It works on almost similar principle of light scattering principle, and third one is modified audio pickup measurement, which will give us the idea about the hairiness as well as it predicts the prickliness of the fabric, okay, prickle sensation. And this low pressure compression testing, it is a Kawabata KESF 3 if we convert, if we just modify. So, that will give us the indication of low pressure testing, okay. It is the compression meter we can test. So, applied pressure and fabric thickness data we can, from there we can get when the bending of fiber protruding from the surface takes place during compression. So, that protruding fibers bending, from that we can get idea about the presence of hairiness. And this is the, it is a laser hairiness meter. It counts the fibers protruding from the fabric surface by laser beam. This is the actually laser beam here, and this one is the fabric, okay, and fabric coming from this point and it goes through the one edge, okay, knife edge type system, then it is winding up here, okay. Now, from there at this point, at the tip point, when it is the light is coming, it counts the number of hairs, okay, and from there one can count the hairs present. The sensitivity of the instrument is adequate only for coarser and stiffer hair. So, that limitation of this instrument, if the hairs are coarser and stiffer, it is projecting beyond the surface in straight fashion, there is no bend, and so in those cases it can the instrument measures actually accurately the surface hairiness of fabric. Another technique is a modified audio pickup technique, which the result gives the idea about the prickle sensation of fabric, okay. It measures the mean force per contact with the protruding fiber. So, that will measure protruding fiber, and this technique may be the most effective measure of fabric prickliness, and the technique is the result obtained from this instrument correlates well with the subjective perception of fabric prickle, which is directly related with the hairiness, yarn hairiness or fabric hairiness, and this is the schematic diagram of the instrument. Now, this is the fabric sample with protruding hairs. It has got two sensors, one is its stationary audio stylus. So, this is basically it measures the number of hairs here and the bending force. Actually the hairs are projected and it measures the number as well as the bending cantilever bending force of the hairs, and normal load is placed, and here the buckling force of the hairs are measured, okay. The two measurements are there simultaneously here. Now, the fabric surface moved under stationary audio stylus. So, this is the audio stylus here and this the fabric moves in this fashion, okay. That has been pulled, from which the signals are obtained from the contact between this point and the protruding fiber, and this creates some sound and some perception is there, and that will give us the idea about the stiffness of hair and also number of hairs, it will give some idea, okay. And in addition, so two classical models are considered here. One is that loaded cantilever model, that is by the audio stylus model. Another is that it is a Euler column, it is a buckling force. So, buckling force is calculated So, bending force and critical buckling force they are calculated, and that these are actually generated from the hairiness of fabric surface, which actually in turns coming from the yarn hairiness, and this gives that the critical buckling force of the protruding fiber ends is responsible for stimulating the mechanoreceptors. Those are responsible for pain sensation, that is a prickle sensation. It gives idea, and this is the model. Okay. Now, the principle is that this is a normal fiber, and here is the bending force we can measure, and also buckling force we can measure with this. So, critical buckling force is actually given by the equation P E is the buckling force, and where E is the Young's modulus of the fiber. Now, so if the Young's modulus, initial modulus of the fiber is high, then it will create higher buckling force, that means it will give the prickle sensation. I is the moment of inertia, that means it is proportional to the fourth order of diameter. So, if the fiber diameter is more, as we have discussed earlier also, if the fiber diameter is more, it will create hairs, and if it is hair is created and it with a for more higher diameter, it will give higher moment of inertia, and the buckling force will be more, and that means it will create the prickle sensation, and also the length of the hair. Now, length here for prickle sensation, the length of the hair, if it is less, then it will give us more buckling force, critical buckling force, and that will actually in turn result prickle sensation. Okay. So, it is inversely proportional to the square of the length of the hair. So, I think we have covered the hairiness of yarn and fabrics in detailed here, and we have seen various techniques of measurement and their implication in product, final product, and we will end the session here. Thank you.